This is Chapter 6, Part 4, and we're going to talk about collisions. So what we mean by a collision is a short duration interaction between two objects. Now keep in mind the interacting objects don't need to be initially at rest for conservation of momentum to be valid. The example I have here is if we have a ball that's moving to the left with a certain momentum and it crashes head-on with an identical ball moving to the right with the same size momentum. Before the collision, the two momenta are equal in size but opposite in direction. Because they're vectors, they're going to add to 0. Now, after the collision, the balls are going to move apart with equal momenta in opposite directions. The speed is going to depend upon the type of ball, whether you're dealing with a billiard ball, whether you're dealing with a lead ball, maybe a ball that's a soft putty and might stick together. But in all cases, the two momenta are going to be the same size and in opposite direction. Therefore, your total momentum is going to remain 0. Now, whenever you have an accident, the investigator will use conservation of momentum to reconstruct the automobile accidents. We can't really use Newton's laws to analyze the collision because we don't know the details of the forces involved. But we can use conservation of linear momentum because that's going to tell us that regardless of the details of the crash, the total momentum of the two cars will remain the same. So here's a picture showing a rear-end collision. We're assuming that the front car was initially at rest. The two cars locked bumpers upon impact. So investigator would look at the skid marks made after the collision, the type of surface, and then the total momentum of the two cars could be calculated. So which brings us to our first type of collision we can have, and that is an elastic collision. So in this case, we have two objects whose momentum and kinetic energy are conserved. As you can see by the pictures on the right, they are going to approach each other, they're going to collide, and notice how they bounce away from each other. So the formulas you can see are given the speed of ball A finally, and also on the bottom the speed of ball B finally. Now I will not have you solve for any other variables than the final speed of A or the final speed of B because it can get a little complicated. So let's look at a sample problem. We have a 10 kilogram block sliding to the right across a frictionless floor at 4 meters per second. We have a 5 kilogram block traveling to the left at 2 meters per second, such that it's going to hit the other block head on. Okay, and you can see the picture along the bottom of the screen. After the collision, the 10 kilogram block moves to the right at 1 meters per second, and you're asked to find the final speed of the 5 kilogram block. So it's a momentum problem. So we want to find our initial momentum, which is going to be the 10 kilograms times the speed of the first block, which is our 4 meters per second, plus our 5 kilogram of our second block times the speed of it is 2 meters per second. Now, because it's going toward the left, that 2 meters per second is going to have a negative sign by it. So when you plug that into your calculator, you should get 30 kilograms meters per second. Now, our final momentum is, we can see, is going to be our 10 kilograms of block 1. And notice the speed is now 1 meter per second. And that's going to be plus our 5 kilogram block. And we're going to say V2 final because we don't know it, and that's what we're trying to calculate. So we have 10 kilograms meters per second plus 5 kilograms times V2 final. So we know conservation tells us that initial momentum is going to equal final momentum. So therefore the 30 kilograms meters per second has to equal our 10 kilograms meters per second plus our 5 kilograms V2F. We're going to subtract 10 kilograms meters per second from both sides, and that's going to leave us 20 kilograms meters per second, so those cancel out. Then we're going to divide both sides by 5 kilograms. That's going to cancel. So then V2F is going to equal 20 kilograms meters per second over 5 kilograms. So that's going to give us a value of 4 meters per second. Okay, now we have a 10 kilogram mass, and it's colliding elastically with a 2 kilogram mass. So we know we have 2. So let's say our 10 is going to be our mass A. It is traveling, so velocity of A is 2 meters per second. It meets and collides elastically with our B, which is 2 kilograms for a mass, and it is traveling 4 meters per second in the opposite direction, so that needs to be a negative. And you're asked to find the final velocities of both. So we want to go get those formulas that we talked about under elastic collision. So VAF is going to equal MA minus MB over MA plus MB times VAI plus 2MB over MA plus MB times VBI. So therefore VAF is going to be 10 kilograms minus 2 kilograms divided by 10 kilograms plus 2 kilograms times 2 meters per second plus 2 times 2 kilograms divided by 10 kilograms plus 2 kilograms times a negative 4 meters per second. So when we plug this all in, we're going to get 0, which basically means the collision stopped this mass. Now we're asked to find VBF, and that is going to be 2MA over MA plus MB times VAI plus MB minus MA over MA plus MB multiplied by VBI. So we put in our numbers, and the final velocity of B is going to be 2 times 10 kilograms divided by 10 kilograms plus 2 kilograms times 2 meters per second plus 2 kilograms minus 10 kilograms divided by 10 kilograms plus 2 kilograms times minus 4 meters per second. And when we plug all that in our calculator, we get 6 meters per second. Okay, that ends part 4 of chapter 6.